Hi, my name is Guy Hawkins, and this is a pre-recorded presentation for the 2021 meeting of the Society for Mathematical Psychology. In this presentation, I'm going to discuss the many different ways in which time influences decision processes. And by the end of the presentation, I hope to convince you of two main things. The first is that time has an impact in different ways on how we make decisions. And so I'll stage this through different layers, including how time influences processes used to make individual decisions, processes about how we make decisions across a set of trials under some constraints, and also how the natural passage of time changes how we make decisions. The second thing I hope to convince you of is the kind of greater psychological explanations that we can gain through the use of combining experimental data and cognitive modeling. To start with, we might consider the different ways in which decisions are influenced by different types of contexts. So the context could be something about our cognitive state or our emotional state or well-being. It could be related to our physical well-being. These are all kind of person-level contextual factors. The way we make decisions is also influenced by our broader environment. This might be the social context or your cultural context, and even the political environment influences how we make decisions. In this society, we've had quite a lot of focus on other kind of stimulus-related factors and how they influence decisions, things like the framing of information or the particular ways in which we present it. There's many other factors that I won't go into detail in this talk because each of these are their own literatures. Instead, I'm going to focus on the temporal context. And so you might ask, well, why time? I think there's many answers to this question, but I'll outline just a couple on this slide. And the first is what I might think of as the local view. And that's that all decisions are made under some degree of time pressure. There might be lower time pressure in some occasions compared to higher time pressure in others. But the fact is that no decisions occur in a vacuum. And in that sense, time is relevant to all decisions. The broader view is that our psychological processes change over time. We're not static. And if we want to get a complete understanding of decision-making or in any kind of cognitive function, we do need to deal with time. And I'll return to this point at the end of the presentation. So from at least these two perspectives and others, time is, in a sense, like a unifying feature of different types of decisions. It always has an impact. And in this sense, I think it's an important thing to be considering. In this talk, I'm going to cover three main themes. Three main questions. The first is, how does time impact individual decisions? The second is, how does time impact a set of decisions? And the third is, how do decision processes change over time? So I'll go through these in order, but just before I start with that first one, there's a little bit of background information to give. And so this is related to what are the psychological processes driving individual decisions? In this society, we have quite a long history with particular types of models of decision-making, and I'm going to continue in that theme throughout most of this talk. And so these are models of rapid choice, often in perceptual domains. So questions like, do the lines on this Gabor patch to orient to the left or to the right? Relates to lexical decisions, like whether this string of characters forms a valid word or if it's a non-word. And it could be many other perceptual or cognitive tasks. It might be related to short-term memory or recognition and many others. This kind of data in rapid choice context has, for a long time now, been explained through evidence accumulation models or sequential sampling models. And I've got on the slide here the canonical diffusion model of decision-making. And the idea being that when we're presented with a stimulus, we dynamically extract information from that stimulus and we accumulate or collect it in some kind of evidence counter. And that process continues until we reach some predetermined evidence threshold, shown here as those dashed horizontal lines. And once we cross that threshold, that triggers a response for the response that was mapped to the threshold that was crossed. So that predicts a choice. And the time taken for the process to reach that threshold dictates a decision time. And in this way, sequential sampling models account for the joint distribution of choices and times. And these classes of sequential sampling models have explained many features of speed of decision-making behavior. And we have a great evidence base documenting that over many years. And so with that, I'll turn to timing in individual decisions. And so I became interested in this question a few years ago, but at that point, the literature wasn't really asking this question. It was more closely linked to how do people deal with evidence in individual decisions? Or do they use different criteria based on the evidence throughout the course of an individual decision? And so this leads to a popular class of sequential sampling models, which are known as collapsing thresholds. They're sometimes referred to as urgency signal models as well, and there's some parallels between the two, but throughout I'm going to join them together under the umbrella term of a collapsing threshold model. And the idea is, just as I described before, for the fixed threshold models, except with a collapsing threshold, the idea is that our evidence criteria, so the threshold that we use to trigger a response, might change throughout the passage of an individual decision. And that's shown here with these solid curves that are kind of start at the same level as the fixed thresholds, and they gradually and dynamically move toward each other. In this sense, we can say these thresholds are collapsing as a function of time within an individual decision. So the idea here is that your evidence criteria for trigger and response changes as a function of time. And so this leads to different predictions in data. If we consider these two sample paths of the diffusion model under a collapsing or a fixed threshold, we see that they lead to the same prediction for the choice, but at different response times. Collapsing threshold models have had at least two strong theoretical motivations that I'll focus on here. And that's that they provide the optimal decision policy under different conditions. So one of those is that collapsing thresholds provide a strategic and optimal adaptation to decisions in the presence of deadlines. And so sometimes we have a decision stimulus presented, and there'll be some either fixed or variable deadline after which a response can no longer be made. And so it's been shown that under these different deadline conditions, the optimal policy is to collect as much information as you can, but collapse your thresholds to the midpoint to ensure you give a response before the deadline has passed. And you should just adapt this to however long it is until the deadline occurs. The second theoretical motivation has been about maximizing reward rate. And so this refers to the situation where you have a fixed amount of time to complete as many decisions as you can. And the goal is to get as many correct as you can, or to get as many rewards. And that tends to maximize the reward rate. We know it's been proven that in environments where there's only ever a single difficulty level of the decisions you complete within this fixed time, a fixed threshold model optimizes your reward rate. However, when there's mixed difficulty decisions within this environment, a collapsing threshold model optimizes reward rate. And that's because if every decision that's correct gives you the same amount of reward, well, you should minimize the time that you spend on decisions that have a low probability of success, those hardest decisions, because you're not that likely to get it correct anyway. And instead invest your efforts on those trials that have easier decisions. And so in this sense, you should collapse your thresholds, because if you haven't hit threshold early, you're more likely to be in a harder stimulus difficulty condition. And so you should bail out of this decision and continue to the next one sooner. These are two theoretical motivations for collapsing bounds. And the question I'm interested in is, do decision makers actually use them when it's optimal to do so? To answer that question, we rely on there being a signal in data that discriminates between the two theories, between fixed thresholds and collapsing thresholds. And there's a few, some are quite subtle, but the primary factor that discriminates between the two is the shape of the response time distribution. So in the center of this figure, I'm showing you the schematic of fixed and collapsing thresholds from before, and above and below I'm showing distributions of response times. And you can see that under a collapsing thresholds model, shown in the solid blue and orange curves, there's a truncated tail to the distribution. And so the main signature that differs between the two types of threshold models is the shape of that distribution and the degree of skew. So we've tested these different theoretical motivations for collapsing thresholds. And so that first one was about decision deadlines. And we asked participants to do a standard perceptual judgment task with a known fixed deadline. And so this was a deadline that does cut off decisions in this particular environment. And so people needed to collapse those thresholds prior to the deadline. And we think of this as a scenario where it was really obvious to participants there was a deadline, they knew about it, and it never varied across trials. So we were trying to maximize the chance that people would use a collapsing threshold. And so what I'm showing here is separately for every participant in our experiment, so that's on the x-axis, the weight, the model weight, comparing fixed thresholds in orange to collapsing thresholds in blue. And we see a majority kind of evidence overall for collapsing thresholds. It's not hugely convincing, but on average, we see evidence for a collapse. And on the left here, I'm showing you the estimated thresholds for the group level. And so this was a model estimated separately on individual participants. If we aggregate the threshold estimates from each participant and display them, this is what we get for the population. And so we've got the same color mappings for the two models here, and the dashed vertical line is showing you the timing of the deadline. And so what we see is that people did collapse their threshold before the deadline occurred, but not in an optimal way. If participants were performing optimally, that threshold collapse should go to the midpoint before the deadline. And this would ensure that people always give a response. So we might ask here, what signatures in the data discriminated between the two models? And so here, I'm going to show you 4 panels, and each one shows you a different summary statistic. And so we see here that there's very little difference in accuracy prediction between the models. Same for mean RT, same for the variance in the RT. But what we see is the skew differs. This is exactly the signature we were aiming to pick up on. And we see that the collapsing threshold model nails the skew, and the fixed threshold model overpredicts the skew. This is why we saw an aggregate weight toward the collapsing threshold model. So something else we see is that if we manipulate different types of deadlines in different conditions, participants are sensitive to that. So this is a reassuring sanity check. So under no deadline, we might get some minor collapse, but not really. In the green, we have a condition where there's quite a slow deadline. And in the red, a very fast deadline. It's really quite high time pressure. And we see that the degree of collapse in these models kind of scales with the extremity of the deadline. Now on to our second motivation. So when participants were aiming to maximize reward, in this task, we set up an environment with 1-minute blocks where participants were instructed to maximize the number of correct responses. And we manipulated the difficulty within this environment to quite extreme levels, from chance in the sense that there is no reliable perceptual signal through to really quite high, easy decisions, where participants averaged around 95% accuracy. And we again conducted the same procedure, and we see overall, the model weight is actually towards fixed thresholds. We see a mix across the two, but on aggregate, it's fixed. And again, if we look at the estimated thresholds, we do see some degree of collapse in the aggregate, but it's not particularly strong. We can again consider the summary statistics in data. And what we see here is that the collapsing thresholds model is doing better at picking up mean accuracy. But neither of the two models are really doing particularly well for the other 3 summary statistics. Overall, the fixed threshold model is slightly closer to the data, but in each case, both models underpredict the key effects in data. So returning to our question, do decision makers use collapsing thresholds when it is optimal to do so? Well, I'll tell you kind of, but not much. And when they do use collapsing thresholds, they're not using it optimally. We saw this in the deadline data where people should collapse those thresholds to 0. And so if we kind of combine these effects and some others, here's like a brief summary of at least some research that I've been doing on this topic. And so if we have speed accuracy trade-off manipulations, we see that, under deadlines, people seem to use a collapsing strategy. Under like verbal cues, be fast, be accurate, people seem to use fixed thresholds. if you encourage people to maximize reward rate, the evidence was a bit mixed. If we make the presentation of the evidence kind of time dependent in the sense that sometimes the same information appears slower than other times, then it looks like people are kind of using a collapsing threshold strategy. If you instead make the evidence kind of scale with time, so early in a trial, there's not much evidence, later in a trial, there's more evidence, people seem to use fixed thresholds in that case. And so overall, my impression from this is it's not particularly convincing in which situations people should use the different strategies. Which leads me to ask, well, where do we go from here? We know that time impacts individual decisions, and collapsing thresholds explain some of those effects, but not all of them. But for me, one of the challenges here has been that there's a bit of a schism in the sense that it's an either-or question. And I know I've contributed to this debate, but is there evidence for fixed thresholds or collapsing thresholds? And there's not much unification between the two. And I find that this just isn't very conducive to advancing our understanding of decision-making. Another point I haven't really touched on here, and it is a tangential one, is that it turns out it's actually pretty challenging to apply collapsing threshold models to data. It can be done, and it can be done well, but it's not the easiest approach. And this can be an issue if we ever want to use these models toward applied questions rather than experts in applying these models. My argument here is that we need an integrated theory of how time influences individual decisions. And so this is a question that I've targeted more recently. And the idea here is to build a complete mental representation of time into the decision process. And in doing this, we've integrated sequential sampling ideas from two different literatures to make a new model. And so that's the literature on decision-making and on temporal cognition. Both of these theories conveniently use sequential sampling models, and formalize them, and apply them to data. But they've mostly evolved kind of in parallel across a lot of decades with kind of minimal crosstalk. So in combining the two here, Andrew Heathcote and I have come up with a model that we have called the Timed Racing Diffusion Model, the TRDM. The TRDM has a simple sequential sampling setup. So we assume a race model structure. So there's a different evidence accumulator for each of the response options. So in this schematic, we're looking at a choice between two options. And we call this the evidence process. The addition for the TRDM is quite simple. It's that we used to have another accumulator. So for a decision between n options, we have n+1 accumulators. And that +1 accumulator on the end represents the timing process. And so instead of accumulating evidence from the stimulus, it's about accumulating time or monitoring the passage of time while we're making a decision. And the idea being that we have some threshold amount of time we're willing to wait before making a decision. And we may trigger a decision based on too much time has elapsed, even if we haven't accumulated enough evidence to cross a predetermined evidence threshold. And in this sense, we might trigger a decision based on how much evidence we've collected or how much time has passed. In our work so far with this model, we have used a very simple decision rule for when the timing process terminates the decision, but many others are possible. So a quick summary of some of the key points of the TRDM is that it's simply a race between one boundary diffusion processes or shifted walls. The components of the model have a history in two different literatures and we're just joining them together. It generates novel, testable predictions for decision and timing phenomena. It has a simple psychological interpretation. We have no cross-trial variability parameters in the model. It's simple to estimate, has an analytic density function, so it's very rapid. And it gives us a new psychological interpretation of decision-making. So in this model, we have information and time-dependent stopping rules. And so by mentally representing time in decisions through the lens of the TRDM, we've been able to explain many decision phenomena. These include classic effects like the speed-accuracy trade-off, decision difficulty. It's other effects like decisions in the presence of deadlines, whether those are externally imposed by the experimenter or internally imposed, like some time limit we're willing to commit to a decision. Also other features like anticipatory decisions and non-decision phenomena, like how people estimate intervals. I've presented some talks on this before from last year's mathematical psychology meeting, and you can find some details at this YouTube link. I'll briefly go through how the model accounts for some of these effects without giving an exhaustive overview. So if we consider that a standard speed accuracy trade-off experiment where sometimes participants are asked to be speedy and other times they're asked to be cautious. And so when you do this, we see a different collection of parameter effects here. The two strongest that we find though are that when instructed to be fast, people have a shorter non-decision time, and they increase the rate at which they can perceive the passage of time. They're less willing to wait for a decision. We see two other effects that also occur, but they're less strong. So things like increase in the mean drift rate across all of the evidence accumulators and a decrease in the evidence threshold. And you'll see by these Z scores here that the traditional effect ascribed to the speed accuracy trade-off manipulation in a change to the evidence threshold is actually the weakest effect that we observed in the TRDM. So we can illustrate how the TRDM accounts for these effects as well. So on the speed emphasis here, I'm showing a conditional accuracy function. And so on the x-axis, we just have the response time. And on the y-axis, it's the accuracy. And the black line there showing how accuracy changes across different RTs. And the posterior predictive distribution of the model captures that general pattern. We can then do inference, latent inference from the parameter estimates. And showing in the lower panel, what I'm showing is the relative likelihood or the posterior probability of each accumulator being at threshold conditioned on a particular response time. And so the easiest one to interpret there is that the error accumulator is just always low. People were not that likely to have the error accumulator hit threshold at any given time. Importantly though, it still declines as RT goes longer. What you'll see is that the earliest RTs that the accumulator corresponding to the correct response and the timing accumulator have close to equal probability of being at threshold. And we see a rapid divergence where the correct accumulator increases and then slowly decreases as RT grows longer. And we've seen almost mirrored pattern in the timing process. And so it's this collection of changes as a function of timing that allows the TRDM to account for different effects like fast errors, because the timing accumulator was likely to hit threshold very early, but not so much later. We can also infer from this that 27% of the trials were terminated by the timing accumulator. We can compare this to the accuracy condition, where overall we see the conditional accuracy function is much higher, as you would expect. And we see much greater separation of the correct and the timing accumulators as a function of the response time. And as a result, when people are instructed to be accurate, only 15% of the trials are predicted to be terminated by the timing process. And so this, we can infer from these estimates that people kind of scale the speed of their timing process. And so when you ask them to be fast, they're more likely to make a decision based on just the passage of time. And they're less likely to do that when they're asked to be careful. So the TRDM also explains empirical effects that were previously thought to require collapsing thresholds. And so in particular, thinking about things like the deadline example I talked through earlier. So in the TRDM, the decision maker could calibrate their timing process to ensure that it terminates before the deadline, at least on average. So to demonstrate this, we have applied to our model to data that I'll revisit in the last section of the talk, but that's one where there's been very strong evidence for collapsing thresholds. And this was a data set with 2 monkeys that completed many perceptual decisions. And what we found is that we get equivalent goodness of fit to data for the TRDM and the collapsing threshold models, but a qualitatively different psychological interpretation. And that is that our timing process means that we don't engage too long in challenging decisions. And so I'm showing you these same kind of relative likelihood plots as for the SAT manipulation. And so in the easiest trials for Reutemann and Shadman's monkeys, you see accuracy was very high. And so as a response, we expect the accumulator corresponding to the correct answer to also be very likely to be at threshold for any given RT. And that's the case, but we do see a decline in that effect as RT grows longer, and the timing process becomes more likely to reach threshold. As we start increasing the difficulty of the decisions, we see that for fast RTs, we're very likely to have correct accumulator at threshold, but as RT grows longer, it's less likely to be at threshold and we're more likely to make a decision based on the timer. And this effect continues as we go through the harder trials, and in particular trials with no signal. There's literally no perceptual signal on which to make a response here, so it's chance accuracy. And we see that people are very likely to just be at threshold for the timer for a large proportion of the range of RTs. The other thing we can do here is look at the percentage of trials predicted to be terminated by the timer. We can see that when the stimulus is easy, it's quite a small proportion, but as the difficulty increases, we're getting up toward 2/5 of the trials to be triggered by the timing process. So an interim conclusion from this work is that time impacts psychological processes underlying individual decisions. And this can be through externally or internally imposed effects. So things like an external deadline or a time limit I have in my own head, even if there isn't a deadline imposed upon me. Collapsing thresholds models, overall, they really think about time through the lens of evidence. And by that, I mean that if you want to change your evidence criteria as a function of decision time, you need to be monitoring something about time to be able to do that. It's kind of a two-step process. Collapsing thresholds do have some clear support in some contexts, and not so much in others where we might expect that they would be used. And there's motivations grounded in optimality. They're just not clearly supported in data, at least in the investigations where we've tried to find support for them. In contrast, the TRDM provides an explicit representation of time in how we make decisions. And it has a strong explanatory scope relative to fixed and collapsing thresholds models. And one reason I like to use the TRDM is that we can use the same framework to understand when time strongly impacts individual decisions and when it doesn't have such a strong impact. And in that way, we can use one architecture to investigate these differences parametrically and avoid these questions of fixed or collapsing thresholds, where it's one or the other. The second theme that I'd like to talk through is how people deal with time across a set of decisions. And to give that a slightly different pitch, the real question is, how do people allocate time to individual decisions to achieve a goal across a set number of decisions? And for this question, I'm going to motivate this based on that idea of maximizing reward again. So as a reminder, that's when we have a fixed amount of time to complete any number of decisions. And the goal is to maximize the number of correct or rewards across that sequence of decisions. So a question that I often ask myself is, well, but who's maximizing reward and when do they do so? So I've just given some examples that people don't necessarily try and do this, or at least it's not a natural mode of operating. People can maximize reward when you give them a lot of help and instruction and tailored feedback. They can get there. But the fact that we need to try very hard to get them there suggests it's not a default mode of operating. Yet animals are surprisingly good at it, and it makes a lot of sense. If we think about how animals forage in the wild, they need to maximize reward, right? So they need to go find the food before nightfall or before the predators find them. So they need to know which source to forage from to get the food in the amount of time they have available. Yet with people, maybe we're asking the wrong question. Maybe time is more salient than reward. And so people are doing something about minimizing time rather than maximizing reward. And so my argument here is that time is a contextual cue, and that people would change their decision strategies when they're exposed to different decision environments. And a prediction that falls out of that is that the same stimulus information presented, but in different temporal contexts, will be approached differently. And so here I looked at this quite a few years ago now with a very perceptual judgments in an environment where the difficulty changed quite markedly, and we manipulated difficulty by the number of distractors from which people had to identify a perceptual target. And so in one of the experiments that I'll talk about here, we manipulated that set size or the number of distractors randomly from one trial to the next. And so what you'd expect here is that when there are a few distractors, people should be more accurate than when there were many distractors. And that's exactly the effect that we find here. Then if we consider how long it took people to make these decisions, we find an increasing mean RT from few to many distractors. And the increase follows very closely an old effect known as Hicks' law, where the mean response time increases linearly with the logarithm of the number of alternatives. And so this is all pretty straightforward. What we did then was a manipulation was one of those first things we teach undergrads, which is whether we manipulate something between subjects or within subjects. And so in the second experiment, each participant saw just one set size. And then we manipulated this across many different groups of participants. And we found that the mean RT was drastically different across these two experiments. And so to the extent that for those hardest conditions, the largest set size, the RTs were almost double. And so this was quite striking to us. These were first year participants that weren't being incentivized in any way other than course credit. Yet we saw such a massive difference in their RTs. What we also see here is that the accuracy was very different, and we actually no longer saw this decline in accuracy as a function of set size. And for those hardest decisions, again, the difference was almost 20% accuracy, which is really quite stark. And so it looked like people were adjusting the accuracy or the way they were dealing with this task as a function of the context that they were finding themselves in. And between subjects manipulation, there was no context. You only ever saw one set size. And it turned out that on average, across all the groups, the accuracy is really quite similar. And we found that this principle replicates across different time-based manipulations. So in that example, we're manipulating difficulty with the set size, which impacts time, but that's indirect. We can do better here and directly manipulate the task timing. So in this case, we had a task where information accumulated externally in the stimulus display. So these tokens collected at a particular rate, and the participant was asked to identify which option was accumulating tokens at a greater rate. And they got some kind of feedback about that. We manipulated the rate at which these tokens appeared on screen, which we call the drop delay. So in the fastest condition, a new token would appear every 250 milliseconds, and in the slowest condition, it was over every 600 milliseconds. And we see when people experience all of these rates of information presentation, that they're collecting less information prior to making a decision when that information comes online slower. And so again, we'd see exactly what you'd expect when you collect more information, be more accurate in these faster conditions. Again, that's not too surprising. The interesting effect comes when we then manipulate the drop delay completely between subjects. And so the different numeric symbols on this figure represent the speed at which information was presented. And so each person only ever saw information accumulate at one speed, but they made decisions about many set sizes. And so we see that the mean number of time steps that people wait to collect information was approximately the same across all conditions, which led to approximately the same accuracy. But then the stark difference was then that meant that the RTs across groups was again drastically different, such that those people that saw information presented the slowest were took twice as long to make these decisions as the people that saw the information collect the fastest. Again, from the participants' perspective, there was no motivation to try to do this. It was first year participants for course credit, completing the experiment online, yet we see this drastic effect in the actual time taken. So from these experiments, we conclude that people adapt their decision strategy to the temporal context that they find themselves in. But to what end? Like, what's the goal in doing this? So we investigated this in a few different ways, and the kind of psychological explanation that we landed on is one where people actually learn a very clever strategy. So to explain this, I'm just replotting the data from the first within subjects experiment condition that I discussed. And so the crosses represent those data with the accuracy on the y-axis and the choice set size on the x-axis. And so if we suppose we have a goal for the environment where we want to have a particular accuracy rate averaged across all the conditions. So let's say that's 60%. One way you could do that is to be 60% accurate in every condition. And so that's shown with the dotted gray line here, the horizontal line. And we see under some assumptions of a particular simple cognitive model that gives a mean RT for the whole experiment of a little over 16 seconds. But it could be 60% global accuracy with many different kind of rules for how accurate you should be within each set size. So another version you could do is what I call the steep 60%, where we have dashed gray lines. And so you could be very accurate for low set sizes and very inaccurate for large set sizes. So a very steep change across conditions. That can again lead you to 60% accuracy, but it turns out that's actually slower than having a fixed accuracy criterion across all of the set sizes. What we did was, using the assumptions of this model, we then did a brute force grid search to say, find us the criterion accuracy level for each set size that would minimize the global mean RT, subject to being 60% accurate. And the result of that is shown with the solid black line here. And it turns out the fastest mean RT you can achieve in the experiment is actually extremely close to the data. And we call this idea the min RT hypothesis. And so what we conclude from this is it looks like people are doing something like conditionally optimal decision making. They're not maximizing reward, they're minimizing total time subject to that global accuracy goal. And so in this sense, it seems like time is really quite salient to these participants, not the reward. So our conclusion from this work is that the same information but presented in different temporal contexts can change how we act on that information. People appear to make conditionally optimal adjustments, at least in some situations. And in current research, we're looking at how quickly this min-RT idea emerges in data and what kind of decision strategies would allow people to learn that conditionally optimal global strategy. The final theme I'll cover in this talk is how do decision processes change over time? My first case study here returns to the idea of collapsing thresholds. And so if we just drop for now this idea of optimality considerations, we can then see, when do people use a collapsing threshold? In fact, when do monkeys use one? And so we did a large scale investigation. We had many data sets that came from different labs using different tasks, different numbers of trials, different numbers of sessions. And we just wanted to apply the models to data and see, where do we find evidence for collapsing thresholds? This was across a range of perceptual judgment tasks. And I'll present the evidence like this, where we'll show individual participants along the x-axis, some posterior model probability on the y-axis, and different shades of blue representing the different models. And so I'll focus on the light blue and the darker blue here for fixed versus collapsing threshold models. So we say overall in humans, there tends to be a weight of evidence toward fixed thresholds. We see one data set that I'm going to return to in detail soon, where we see strong evidence for collapsing thresholds. And we can again plot the estimated thresholds from each experiment, and they're on the whole mostly fixed, except for that one with collapsing thresholds. We can look at the same thing for the data sets with monkeys. And what we see is overall quite strong evidence for collapsing thresholds, and some evidence for an urgency signal, which is very much alike a collapsing threshold. And again, if we look at the estimated thresholds averaging across the monkeys in each data set, we see some that have quite strong evidence for the collapsing thresholds. The others look fixed, but also one of those is because there's actually evidence for an urgency signal, which is not represented in these average threshold figures. So if we wanted a sensationalist conclusion, it would be there's a species difference. Monkeys and humans make decisions in different ways. But I just think that's so unlikely. And so the thing I think is far more likely is that there's methodological differences between how we conduct studies with humans and how we conduct studies with monkeys. And in particular, I'm going to focus on the impact of time-based incentives and the timing structure of the decision environment as the factor that changes. And so this is completely post hoc based on the results that I just showed you between humans and monkeys. But if we do some kind of grouping there, it might give us hypotheses about what differs between the different results. So if we consider the amount of task training the participants had completed, and we do that based on where there are very few testing sessions, we see mostly evidence for fixed thresholds. If we then split it into where we know there's a lot of practice, so that's all of the monkey data sets, we see a weight toward collapsing thresholds. And there's this one human data set that's quite peculiar, where the method actually makes it clear that the participants are well trained because they're all members of the same research group, but not how well they're trained. The second thing I'm going to focus on is something that I call the feedback delay. And this is a passage of text from Roitman and Shadlin in 2002 in the method, where it says that there was a reward withheld for a minimum of 800 or 1200 milliseconds, depending on the monkey, after the onset of the random dot motion perceptual stimulus, no matter how quickly the monkey indicated its choice. So it's whichever came later, the response or this kind of fixed reward timing of 800 or 1200 milliseconds. So the reason I focus on this is that that duration is extremely slow for a monkey. The other monkey data sets that we looked at had average RTs around 0.25 seconds. And so if we then do, again, this post hoc classification, we see two of the data sets employed this delayed reward and some amount of practice. And the other data sets, we had some that also had a delayed reward, but no practice. And we find that in there, almost all participants had fixed thresholds. So we combine these two things, the feedback delay and task training, to directly test those kind of post hoc hypotheses we're forming there. And so we had implemented a feedback delay where we withheld the feedback until a response was given or until a minimum time post-stimulus onset had elapsed, whichever came later. So we had two different groups of people, one that received immediate feedback, which is just like how most perceptual decision tasks are run, and one where participants had a feedback delay of 1 second. All participants trained in this task for quite a long time, 10 sessions, where each session had hundreds of decisions. So overall, from each participant, we collected somewhere in the vicinity of 3,500 to 4,000 decisions. And so I'll display the results in terms of the two conditions and also broken down by session, where we applied models in a hierarchical manner independently to each session. So again, we have our estimated fixed and collapsing thresholds, and we can look at this across sessions in the 0-second delay condition. So we can see as we move along, there's not much difference between the two models. And in fact, we only really start to see some kind of collapsing threshold until we get to around session 7. If we do some model comparison here, we see the difference in the DIC value starts to shift around session 7. And so positive values support collapsing thresholds, negative support fixed thresholds. So this is some evidence that time on task or the training influences how we make decisions. If we switch now to the 1-second delay condition, we can see in the first session, there's not that much evidence for a collapsing threshold, perhaps a bit. But as we move along in sessions, we see this start to change really quite rapidly. And by session 10, we have very extreme collapsing thresholds. If we look at the same kind of model comparison between the two models, we see the evidence grows stronger and stronger as session number increases to really quite strongly support a collapsing thresholds model. And so if we align these two things together, we see a dramatic effect of task training to start with, but even more so when it's combined with this feedback delay. So there's two effects of time happening here. One is that there's the timing manipulation within the task when feedback is available, and that has an impact on decisions. And the second is that the people appear to adapt to that feedback delay the longer they've had experience in the task, to adapt a strategy that lets them deal with when that feedback information becomes available. Another side point that came from this is about aggregating data. And so when we have monkeys in tasks like this, they're very hard participants, it's very expensive data to collect. And so when you have a monkey that's able to do the task that you're interested in, people tend to collect very much data from that monkey, which happens across many sessions. Then when it comes time to analysis, that session information is rarely used, and the data are kind of put into one big bucket and aggregated for analysis. So the question of interest here is, do the inferences differ between aggregate and individual session data? And so we answered this with the 0-second delay condition. So instead of analysing each session independently, like before, we pooled all that information while preserving individual differences and analysed it all together. And if we do that, we find a very strong evidence for collapsing thresholds over fixed thresholds, even though the majority of individual sessions were actually of a fixed threshold. And so what this is telling us is that even in cases like the monkey data where they appear to be using a collapsing threshold, it could be that they're using fixed thresholds in every session separately, or even most of the sessions, but the aggregate analysis will lead us to believe that collapsing thresholds were used. And so I think these two effects of time, both the feedback delay and the task training, they matter, because it can seem like seemingly minor methodological details actually could have large impacts on our theoretical conclusions. It's a reminder again of the dangers of aggregating data over units. So in this society, we've known for a very long time about the dangers of aggregating across people. Here we're looking at aggregating across sessions while preserving person information, and we still lead to that same conclusion. So the point why I say it matters is that this feedback delay was actually implemented in the two data sets I'm showing in the boxes here, which are two of the three data sets that have the strongest evidence for collapsing thresholds. And it also matters because Rootman and Shadland's data is freely available and it's been widely used to provide an evidence base for collapsing threshold models. Here's just a sample of articles that have done so, but I find that this is a concern because it provides a kind of skewed interpretation of how much evidence there is for a particular type of decision model in the literature, when a lot of those papers are actually relying on the same data set. I'm going to switch gears now and think about a different way in which time impacts decisions kind of through the natural passage of kind of experience. So what I mean by that is, how does attention change over time? And I've focused for a few years on this idea of mind wandering. And so we hear, this term is used synonymously with other related terms like distraction, attentional lapses, task unrelated thoughts. To me, they're all referring to the same idea, which is that attention fluctuates during goal-directed activity. And we have shifts from external or task-related thoughts to internal or task-unrelated thoughts. Mind wandering can be helpful in some situations, like it can help to generate creative solutions to problems. But in other cases where we have an external goal-directed activity, mind wandering impairs performance. And the most kind of common effects reported for how performance is impaired is that it becomes more variable and slightly more error-prone. In this work, we proposed a model of autopilot behavior, which leads to patterns of rhythmic responding. So we're using autopilot here in the colloquial sense of being able to continue doing the external or goal-directed task, but with kind of minimal attention. So we're still producing responses, just without full attention to the task. And so this model of rhythmic responding had a very similar structure to the TRDM. So it was for a go, no-go task, where there's an accumulator corresponding to the go response and the withhold or no-go response. And it races against another kind of accumulator or node, which is just a rhythmic response. It's just a descriptive statistical distribution. And in this sense, we have a stimulus-related process racing against a stimulus-unrelated process. You might notice the similarities to the TRDM structure. And this model is actually a precursor to the TRDM, which is why this work doesn't have the timing process in it. But nevertheless, there's quite a few similarities in the two. And so here what we tried to do was to consider when this model was applied to the data, could we try and do some kind of post hoc allocation of different trials to the different latent processes? So when were people likely to give stimulus-related versus rhythmic responses? And so what we found is that rhythmic responses were faster and more variable than stimulus-related responses. which is giving a hint that it might be related to mind wandering with those behavioral markers I mentioned earlier. And so another thing participants did throughout this task was that they were occasionally presented with these thought probes where they self-reported where their attention was focused. So on task through to off task. And what we did then was to take participants' self-reported ratings and do a post hoc classification of which process was more likely to have generated a response that kind of just before on task versus off task self-reports. And we find that the probability of a stimulus-related response is much higher prior to an on-task report compared to the probability of a stimulus-related response prior to an off-task report. And there's a quantitative difference here that's really suggesting the model's picking up on some kind of latent dynamic structure about the focus of attention. And so this is really interesting work, but it's all post hoc. There was nothing predictive about which kind of latent process was more likely to generate the response. And this points to a broader problem where almost all applications of sequential sampling models assume the decision process is static, even though we know behavior changes over time. And it's very simple to show. So here I'm just displaying standard perceptual decision-making experiment where we plot the group average accuracy, mean RT, and the SD of the RTs as a function of block in the task. And we see really quite dramatic changes. The change in accuracy of a drop of almost 10% was actually almost the same magnitude as the key manipulation in the experiment, which was about speed versus accuracy instructions. And it's not just the average, it's not mixing of people, because individual participants change in different ways as well. So for one participant, accuracy started at ceiling and gradually decreased. For two other participants, we see that accuracy was more moderate and went up as a function of time for one participant and down as a function for the other participant. And we see similar kind of dynamic trends for the other RT measures. And so this was all within a single session. The decision process seemed to be evolving. And so one way to examine this is to implement different theories of dynamics onto the parameters of the sequential sampling models. And so in this work, we did that in three different candidate ways. One was a polynomial function where it assumes that the parameters of the sequential sampling model change monotonically over time, could be increasing or decreasing, but there's a change. We estimate the parameters indicating the rate of change, and we allow some kind of noise, so it's not purely deterministic. The second candidate function was autoregression, where we allowed the parameters of the model to evolve across blocks as a function of an AR1 process. So this allows the different participants to change over time in different ways, subject to the constraint of the AR1 prior placed on how those parameters can evolve. And the third candidate function was a hidden Markov model on the random effects of the model. And so here for each task that people completed, we had two vectors of their random effects, one corresponding to state A and one corresponding to state B. And we just had a hidden Markov structure dictating the switches through time between those two states. Across three well-cited datasets, we found strong evidence for the hidden Markov model. The people have two latent states and they switch between those two across the task. We can summarize this in different ways. Here I'm showing you one of those datasets that manipulated speed and accuracy, and these panels show individual participants. So the dashed lines, you see the data and how those change for mean RT across blocks of the task. And the solid lines show how the model is capturing those changes. And generally it's doing quite well given the constraint that there's only two latent states. And there's just some probability of switching between those two. Importantly, the solid line that's transparent and horizontal shows the predictions of the static model, or just the standard model, which obviously does not change as a function of time and doesn't capture the data particularly well. Here I'm showing you some posterior inference where we can see what's the posterior predicted RT distribution and accuracy for the two different latent states. And so given the parameter estimates, we can then do some kind of post hoc classification of the two states as one being more urgent, shown in blue, and one more cautious, shown in red. And say, you can see that one of those is faster and slightly less accurate than the other. And on the top right, I'm showing the simulated hidden Markov kind of states for that. So these are just trajectories given the transition probabilities estimated from the model. And we see that there tends to be stickiness staying in the state and then a switch, and more stickiness in the other state. And on the lower part of the right panel, I'm showing the averages across those individual trajectories. And we can then get the dynamic effects in like average predicted state, RT, and accuracy. On this slide, I'm showing you the posterior probability of being in each of the two states. And so in one of these data sets, based on the parameter estimates, we know that it relates to something to do with engagement with the task. And then the posterior probability of being in the more engaged state decreases as the task goes on longer and longer. You see that in the solid lines where the gray boxes indicate some variability across participants. In the other data set, the parameters led us to believe that the two states relate to cautiousness. And then here we learned that as the task went on longer and longer, the degree of caution decreased as participants neared the end of the task. A final thing we learned from these data, a well-known effect in the response time literature, and that's that there's autocorrelation in the RTs. And this is shown in the pale blue boxes for the data, and the model is shown in the solid line. So qualitatively, the model is capturing this autocorrelation, and it does this because trials that are near to each other in time are more likely to be in the same state than trials that are further apart in time. So this is quite a neat finding because we never actually applied the model to the autocorrelation data, yet it still kind of falls out as a prediction. I've given a brief overview of this hidden Markov model here. You can find more information at the YouTube link here, which is from Scott Brown, presented at this conference. So our conclusion from this third theme is that the time on task or the amount of training people receive can change decision strategies. It shifted people from a fixed threshold strategy to a collapsing threshold strategy. Psychological processes are dynamic, but they are often treated or modeled as static. And that the static models, they can provide insight into temporal dynamics. Now, it's that post hoc classification of the probability of a stimulus-related versus stimulus-unrelated process. And in the end, if we explicitly model temporal dynamics, we can get deeper and more precise explanations of behavior. And that's what we found with this hidden Markov model. So to wrap up, I'll return to those two things I started with. The first is that I hope I've helped convince you that time impacts decision processes at different scales, in individual decisions, across sets of decisions, and how those decisions can just change as a function of time. And the second thing is that quantitative cognitive modeling provides us with a deeper psychological explanation about how time impacts decision-making. And across each of those themes, I've told you about the timed racing diffusion model, or the TRDM, as an integrated theory of evidence and temporal processing. I've told you about min-RT, where people can make conditionally optimal adaptations to the temporal context. And I've talked to you about a hidden Markov model, where we built a time series model onto the latent components of processing in the sequential sampling model to account for dynamics. That's all I'll tell you about today. Thanks very much for your attention.